Thank you. So, hi everyone. I am Laia. I'm based in Barcelona, in Spain. And I'm the Chief Science Officer of Ingenii. Ingenii is a quantum computing startup, and our mission is to foster the adoption of quantum computing and quantum technologies within life sciences. And for this reason, we provide some online courses, trainings, and also software tools for data scientists who don't know about quantum but want to get started and want to adopt this technology and to make it easier to treat these people. And one of our jobs as well is to discover what useful use cases are relevant for quantum computing, because as you will see in this talk, not every single problem is a quantum problem. So today, I just wanted to introduce what quantum computing is, why you should care about quantum, and then talk briefly about two use cases that we've been working on at Ingenii. So I think that we can all agree that we are in a computational era. So in the past few decades, we have been developing better and better computers, and we've been relying more and more into computation for our everyday activities and also for research and technology, right? But the thing is that we are reaching some physical and also fiscal limitations with today's computation. And this is because we've been creating and building these classical computers, which are better and better. And we've been doing that by packing more and more transistors into the same amount of space so that we have more computation with the same computers, let's say. But the thing is that we cannot create transistors that are smaller than atoms. That's like a physical limit. So there's only so much more that we can do to improve our current classical computers. And apart from these physical limitations, we also have fiscal limitations, especially with the massive adoption of AI technologies with LLMs and now everyone wanting to train their own AI models. Training those models requires an immense computational power. So it requires having a lot of time, money, and computational resources, basically. So if we keep training these models, the thing is that we will have to spend a lot of energy and time that's not really available. And for this reason, scientists have been thinking about new ways of building computers that could solve some of these limitations. And one of these possibilities is by using quantum computers instead of classical computers. So before talking about what exactly is a quantum computer, I wanted to make a disclaimer because quantum computers are not the next iteration of classical computers. This means that it's not just a new supercomputer that would solve any single type of problem, but rather it's a new way of processing information. It's a new way of designing algorithms. So the way that I understand it is by using this metaphor. So imagine that you are walking on a new island, you're exploring this new island, and you want to like explore all the whereabouts. There are different ways that you can do that. You can just walk around the island. This is going to be probably very slow and time consuming and not very effective. And this is similar to solving a problem by hand. Another thing that you can do is you can drive by car to explore the island. And this is similar to using classical computers. This is going to be faster and more effective. And then another thing that you can do is to rent a boat and just explore the borders of the island and the vast ocean. So what I want to say with this is that quantum computers solve different problems than classical computers. So we don't want to use quantum computers to solve the exact same problems that we can already solve efficiently with classical computers. But quantum computers solve problems that are very difficult or even impossible to solve today with classical computers. And I don't want to go too deep into the physics of how quantum computers work, but the basic idea is that traditional classical computers work with binary code. So the basic units of information are called bits, so you can either have a 0 or a 1. And the analog of this is quantum bits, or for short qubits, which use the principles of quantum mechanics to process information. So for example, a qubit can be in a probabilistic combination of both 0 and 1 at the same time. So you can have a qubit that's 80% 0 and 20% 1, for example. And this property of being in this combination of two or more states at the same time is called superposition, and it's a quantum property. And then another very cool quantum property is called entanglement. And that's what Einstein referred to as spooky action at distance. And the idea of this is that when you have systems of multiple qubits, so you have a quantum computer with multiple qubits, you should not think of the qubits as being independent from one another, but rather they form a physical system that should be considered as a whole. And what this means is that the action of one qubit can affect the state of another qubit. So that information can be transferred in distance. So that the state of one qubit, knowing the state of one qubit, can infer the state of another qubit. And this is something that cannot just simply not be done with classical bits, because bits are independent from each other. If you know if a bit is a zero, it doesn't give you any information about the state of the other bit. And just to give you a sense of what problems quantum computers are good at, I use this metaphor. So with classical computers, imagine that you're solving a maze. The way that you would do that is just by exploring every single different path until you hit a dead end, and then you would start over with a different path. But the thing with quantum is that because of these properties of superposition and entanglement, quantum computers can explore multiple paths at the same time and therefore find a solution much, much faster. So the types of problems that need parallelism, for example, optimization problems where you're searching in a vast space of possibilities, those are the problems that are usually very good with quantum because they can use these quantum mechanics properties to take advantage and make fast computations. Okay, so now another disclaimer. Another thing that people think is quantum computing is 10 years away or 20 years away or, I don't know, a big amount of time away, right? But the thing is that quantum computing is not binary. It's not here or not here, but rather it's continuous, right? So when people think that quantum computer is 10 or 15 years away, they are thinking of fault-tolerant quantum computers. Fault-tolerant quantum computers are those computers which are free of noise. Noise are those effects that happen to qubits that produce errors within the quantum computer. And when we do have fault-tolerant quantum computers, this will unlock a vast range of algorithms, such as, for example, the most famous one is within cryptography and Bitcoin. But the thing is that we can also use quantum computing today to get an advantage today without these fault-tolerant quantum computers. And this is by making use of two different types of algorithms. The first one is what we call quantum-inspired. Quantum-inspired algorithms, they use the principles of quantum mechanics, the algorithm itself, like the algorithm design, but those algorithms still run on classical GPUs. An example of that are tensor networks, if you're familiar with that. So the idea is that with these algorithms, you can run them today on classical hardware and still get some advantage because the algorithm is usually more efficient and more like well-designed than other traditional classical algorithms. And they are also prepared to run on quantum computers so that when you have a large enough, reliable enough quantum computer, you can just translate that algorithm directly and run it in this different hardware. And then we have hybrid algorithms, which use both classical and quantum hardware. So they might start with an optimization problem, break it down to different like sub-problems classically, and then run those sub-problems in a quantum computer. And in this way, you're like getting also short-term advantage by using both classical and quantum hardware. So the idea is that with quantum-inspired and hybrid algorithms, you can still get an advantage today from quantum computing, and in the future with fault-tolerant quantum computers, you will get more and more advantage. So another cool thing about quantum is that it is expected to have one of the highest number of applications and impact within life sciences. So within healthcare and pharmaceuticals and environmental sciences and energy and materials. So there are a lot of applications that you could do in this space, and I would love to afterwards brainstorm with you, understand what you guys are working on, and see if we can come up with ideas to apply quantum to different use cases. But I just wanted to give you a glimpse of potential use cases that you could apply this technology to. So for example, within healthcare and pharmaceuticals, you could apply quantum computing for diagnostic assistance, for example, for medical imaging analysis, for compressing images, performing image classification or segmentation to assist in diagnostic prediction. Then also in precision medicine, you could take multimodal data from different sources and analyze it together within a quantum computer so that you could perform risk analysis in a personalized manner. Then all the field of drug discovery, from discovering small molecules to target validation and the optimization of clinical trials. There are a lot of use cases within this space. And then within energy and materials, anything that's really an optimization problem, like the production process or manufacturing or supply chain optimization or logistics, and then anything related to protein folding or molecular design is also a problem that's usually tailored for quantum computing. And then you might be thinking, okay, can we be more specific? Like, can we actually solve a problem? So I wanted to present two use cases within drug discovery. So the first one is within target validation. And the goal here was to perform accurate predictions of binding affinities. And well, basically the binding affinity is a measure of the interaction of a drug molecule and a target protein. So when you're designing a new drug, and you're looking for like compounds, once you've found the target molecules, you want to do some computational analysis before going to clinical trials. And one of the things that you might look at is this binding affinity to see if this drug is going to bind to a specific protein and not bind to other proteins, because that could have like side effects and like not like produce its function at all, right? So the thing is that to predict the binding affinity of a molecule and a protein, there are a lot of factors that influence this binding affinity. And usually what people have done in the literature is to use AI models, neural network models, to predict this binding affinity. But the problem with that is that while these models are very large, they require a very large number of training parameters to train those, and then you also need a lot of data to train those models, because otherwise you will overfit on your training data. So here what we try to do is, can we use a quantum inspired method to compress these neural networks and therefore reduce the number of training parameters, save time and GPU costs, and also get better accuracy because you don't overfit so much your training data. And in order to do that, we broke this problem down into two subproblems. The first one was to reduce the complexity of, in this case, a classical convolutional neural network. And what we did was to introduce a quantum layer. So we built a hybrid neural network where the first layers and the last layers were classical, and then we put some intermediate layers that were quantum. And these quantum layers, they had much fewer training parameters, so they highly reduced the complexity of the neural network, but they were still able to extract useful patterns from data. And this is because with quantum, you can compress a lot of information with fewer training parameters. And with this model, we achieved like a 20% reduction of training parameters, and that meant a 20 to 40% savings in training times and GPU costs. And then the second part of the project was to try to improve the accuracy of these models. And in this case, what we did is we built a quantum neural network for a fusion model. So we trained two different neural networks, which looked at data in different ways. The convolutional neural network looked at data in a spatial representation. So it looked at the position of the different atoms in space and like extract the information from that. And then we had a graph neural network, which looked at the bonds of the different atoms in the molecules. So these two neural networks extracted different information from data. And then what we did is we took the fully connected layers, and we joined those fully connected layers, and we processed them with both a quantum neural network and a classical neural network. And what we saw is that with the quantum neural network, we achieved roughly a 6% improvement in the performance. And this was mainly because the quantum neural network had fewer training parameters and still achieved the extraction from the data that we needed. So we produced less overfitting on the training data. So in this way, we achieved a compression of the training parameters, and also we achieved better accuracy. So this was for drug discovery. And then finally, we wanted to present another use case, which is for clinical trial optimization. This is a totally different use case. And here, what we wanted to do is to improve the patient stratification process. And the idea is that when you have discovered the drug, you've gone through all the computational analysis and you're ready to go to clinical trials, you're going to recruit patients, and then you will have to separate those patients into different groups, usually like a control group and a treatment group, for example. And the thing is that in order to get statistical significant results, you will want these groups to be as similar as possible with respect to some measurable covariates. So for example, you will want the age distribution to be similar, the gender distribution to be similar, and then if there's any biomarker that's relevant to this drug or this disease, you will also want those to be as those distributions to be as equal as possible. And the thing is that the way it's done now, as we understand, is through randomization. And these randomizations usually induce some biases in different distributions, especially because you're usually not working with millions and millions of patients, but rather hundreds or maybe thousands. So what we did here is, instead of just using randomizations and randomly assigning patients into different groups, can we formulate this as an optimization problem where we ensure that the distributions of different covariates are as similar as possible? So we formulated this problem as a mathematical optimization problem instead of a statistical problem, and then we solved this problem using a quantum computer. And the thing here is that now there are many different combinations how you can split these different groups. So solving this classically is not very efficient, especially when the number of patients grow. But this is a perfect problem for a quantum computer because it's an optimization problem, and quantum computers can like go through the search space in a much more efficient way. And basically, what we found, well, the first thing that we found is that we compared our approach with randomization, and we saw that most of the times there were significant biases for several aspects of the distribution, so for several different covariates. So it made sense to formulate this as an optimization problem. That was like the first result. And then we calculated, we solved this optimization problem using different solvers, including classical solvers, quantum-inspired solvers, and fully quantum solvers. And what we saw is that this, with quantum computers, you could get 2 to 3 orders of magnitude faster results. So these made this problem very scalable, and especially as the number of patients evolve, this will become like very relevant. And now what we're interested in finding is what is the actual impact in the clinical trial success. Because like this problem is important because like clinical trials have a very high failure rate. And I'm sure there are like thousands of reasons why this happened. But we hypothesize, our hypothesis is that patient certification is one of these reasons. And now what we're looking to do is to actually assess the impact of poor patient certification in the results of clinical trials, and what are the economic and health impacts of doing certification in a statistical manner or versus an optimization manner. So these are the 2 use cases that I wanted to present today. We have more. And we're always open to like discover new solutions, brainstorm with people, and collaborate with people within industry and universities as well. So I'd love to hear your questions and involve in discussions. So thank you so much, and feel free to ask any questions, and good luck.
Awesome. Thank you so much. That was super helpful. Even me understanding what quantum computing is and how you guys are applying it. So that was great. Anybody have any questions? Feel free to come off mute and ask live.
I've got one. So I think this is fabulous. And obviously there are a lot of challenges associated with successful clinical trial management, and data analysis is certainly one of those. One thing that is interesting to me is that in my interaction with those who are traditionally in charge of this kind of thing, is that they don't have a very solid mathematical or like engineering background. So how do you anticipate having those discussions and sort of demonstrating the value of this technology to the people who would be running running the clinical trials, and then also to FDA, which also tends to have a fairly low acceptance of novel techniques, so to speak.
Yeah, that's very fair. Well, I mean, what we would like to do, and so we've solved like the technical challenge, let's say, but now we want to solve the impact challenge. So what we've encapsulated this and we've abstracted this as a library that anyone working with any statistical package could use, so that you can just like input the patients and get the distributions, like the two groups or three or whatever number of groups you want. And then what we want to do is analyze how good these groups are. So for example, first of all, by looking at the distribution of different covariates, like just plotting different distributions, see if these covariates are distributed equally. And then I think what's more relevant is when you're actually designing the clinical trial, is there any like anything that you want to statistically prove, right? That you want to prove that this drug works for some sort of population, and for that you will need statistical data. Like you will have to show that you have a p-value lower than a certain number, right? So what we want to show is that with these techniques you can actually get better results at this. And this is not technical in terms of physics or mathematics. This is just related to the success of clinical trials. So that's our goal, to not focus too much on the technology. Like we know the technology, that's all right, but rather how would these people use this technology and what would be the impact? You know, if I answer your question right.
Cool. Any other questions?
I don't have any question, but thank you for the presentation and for allowing us to participate. I've been in quantum computing for a while, and I've gone through a lot of these examples, so it's great to see the progress. So just appreciating your work.
Thank you, Alex.
Any other questions? If not, what I'm going to do is I'm going to put everybody out into breakout rooms, and you guys can all meet each other just for a second here.